Okay, so we've talked a lot about resonance structures, and what we've done so far is kind of just rank them, say, oh, this is a more important resonance structure than that one. How does that impact maybe bond lengths, etc. But now we're actually going to see how resonance can explain chemical properties. So what we're going to look at here is the acidity of ethanol versus acetic acid here, and how that's impacted by resonance. Again, what we want to remember is that more delocalization in the conjugate base means that the conjugate base is more stable. So it was from the stronger acid. So again, we're comparing things here from the stronger acid. So again, we're going to, like, pushing arrows and doing mechanisms, that's what it's called when you're moving arrows around as far as where the electrons are flowing, is such an important part of this course. I want you to pause it, take a minute to do that kind of thing and draw in our conjugate acid, conjugate base, and then think about which one of these you expect to be more or less acidic. Okay, you did that, you're back. Okay, so the base deprotonates acetic acid here. This one deprotonates ethanol. That's going to form our conjugate bases and our conjugate acids. So at first glance, hopefully, again, you're kind of like, oh, this is kind of a pickle. We have O minus versus O minus, the same atom, same size of atom, same electronegativity. So which one of these is going to be more stable than the other? And again, we can kind of approach this from two different directions. One is, how does the rest of the stuff make the acid more acidic? So these are actually two acids that are on your pKa list to know. This one has a pKa of around 16. This one's about 5. So wow, what an enormous effect, right? This is an 11 pKa unit difference. That means that acetic acid is 10 to the 11th times more acidic than ethanol. That is such an enormous effect. So why is that? Why is this more acidic than that? So one thing that you can think about is just what we talked about in the last video, induction. So this oxygen is pulling electron density away from there, putting a partial positive there, and that's going to be shuttling electron density away from this hydrogen. But even to a greater extent, we can also see that resonance is a factor. So if we look at resonance structures of the starting material, we see that in one of the resonance structures, it's not the best resonance structure, but in one of the resonance structures, we can actually put a full positive charge on that oxygen, which means that oxygen is going to pull even harder. It's going to pull electron density even more away from that hydrogen, generating an enormous partial positive there. So that's how we can kind of rationalize that this partial positive is probably bigger than that partial positive because of both inductive and resonance effects. But where I think it's even easier to see why acetic acid is more acidic than ethanol is by looking at the conjugate bases, right? That's what we talked about right here. More delocalization of the conjugate base makes it more stable. That must have been from the stronger acid. So let's look at that conjugate base. Let's draw in any resonance structures that we can down here. So if you haven't already, take a minute, pause it, and draw any resonance structures you see, and then draw the resonance hybrid. Okay, good job. What we can see is that we can draw a resonance structure that takes this full negative charge and moves that full negative charge fully to that other oxygen. So this oxygen doesn't have a full negative charge, it has a half negative charge. This oxygen doesn't have a full negative charge, it has a half negative charge. So the resonance hybrid would look like this, where there are partial double bonds to both of those, and there's a 1/2 negative charge there, and a negative 1/2 charge here as well. So why is this conjugate base so much more stable than this conjugate base? Well, in this conjugate base, that negative charge is fully situated on one oxygen atom. We want our charges to be delocalized. Here, it is split 50-50 between 2 oxygen atoms, which clearly has an enormous impact based on this pKa difference. You can compare that pKa difference to induction to kind of think about which factor has maybe a larger impact on delocalizing charge as well. So that's kind of the last impact that we're going to talk about right now for acidity. And what we see is that those first 2 videos were kind of like, oh, just look at the atom, and based on where the atom is on the periodic table, you can see what's more acidic. And then the second 2 videos were like, all right, now we have to kind of consider the acid itself, also the conjugate base, see where there's more delocalization, see where there might be a larger partial positive on a hydrogen, and those are the factors that help us understand which one might be more acidic. So we'll talk a lot more about this soon. All right.